In this video, we're going to talk about properties of the trigonometric functions on the unit circle. So we're going to add in this special circle. So the unit circle is a circle of radius 1 that's centered at the origin. Okay, so let's just start by drawing that. So there's my circle. And the center there is in the middle. Okay, so what's special about this circle? So we know these outer points. This is 1, 0. This is 0, 1. This is -1, 0. And this is 0, -1. Okay, and the center is obviously 0, 0. So when we're on the unit circle, okay, so first of all, I guess maybe let's just talk about the equation. So if you remember the standard form, the equation is going to be x minus the x-coordinate of the center squared plus y minus the y-coordinate of the center squared. And that's going to equal the radius squared. Oops, the radius squared. So the equation of the circle is x squared plus y squared equal to 1, which might look familiar. Sine squared plus cos squared is also equal to 1. So this is another way you can get that. Okay, but anyway, also on the unit circle, okay, the radius is 1, which means, remember the arc length was r times the angle in radians. So when the radius is 1, the arc length is actually equal to the angle in radians. Okay, so then if I have an angle in standard position, okay, so something like this, so let's say that that's theta, it's going to intersect the circle at some point. Let's call this point x, y. Okay, so this distance is x, and this distance over here is y, and we know the radius is 1. So notice that I have a right triangle here. Okay, so the cos value is the adjacent over the adjacent is down here over the hypotenuse. So that's normally x over r. So I'm just going to write that down here. So normally cosine of theta is x over r, but because r equals 1, then it's just the x-coordinate. Okay, and similarly sine is y over r, but because the r is 1, it's actually just the y-coordinate. So you could actually write this as cos theta sine theta. So that's the coordinates of that point. So this is how we use the unit circle. So then you get a lot of ones for free. Okay, so I labeled these points, but I guess I have a picture down here to use as well. Okay, so 0 degrees is 0 radians. Okay, now the point on the unit circle for 0 degrees is this point here, which is the point, I want to be over a bit. So this is the point 1, 0. Okay, so that's going to be cos of 0, sine of 0. Okay, so that means, so this is the point, so it's the point 1, 0. So that means the cos value is 1 and the sine value is 0. Okay, now 90 degrees is pi by 2 radians. Okay, now 90 degrees is going to be from the positive x-axis to the positive y-axis. Okay, so its point on the unit circle is going to be this one up here, 0, 1, which means the cos value, so this is cos of pi by 2 and sine of pi by 2. So here the cos value is 0, but the sine value is 1. Okay, 180 degrees is pi radians. Okay, so pi radians goes, it's the straight angle. Okay, so that's going to, so its terminal side would intersect this point over here. Okay, so that point is -1, 0. Okay, so that is cos of pi, sine of pi. So that means the cos value is -1 and the sine value is 0. So remember, the sine value is the y value, the cos value is the x value. Okay, 270 degrees is 3 pi by 2. Okay, now 3 pi by 2, let's just get a different color here. 3 pi by 2 ends at that terminal side. Okay, so that's going to be the one at the bottom. So this point is 0, -1. So that's cos of 3 pi by 2 and sine of 3 pi by 2. Okay, so this is the one 0, -1. So cosine is 0, sine is -1 now. And 360 is 2 pi. And now we're going to be back to the beginning. Let's do it in orange. Okay, so 360 goes like that. So that's 2 pi. So again, now we're back to the point 1, 0 again. So cos is 1, sine is 0. Something that's kind of neat, if you drew a straight line from, or a vertical line, x equals 1. Okay, like that. So that's the line x equals 1. Then if you have your angle, so it's in standard position. Okay, maybe it goes like that. Okay, so if this was, oops, if that was theta, okay, then this height, so this would intersect here, and this height, so the y value, so this point is 1 and some y value. Okay, the y value is actually tan theta. So this is 1 and tan theta, which is kind of neat as well. Now, if your angle was, say, over here, okay, that's going to have the same tan theta. So it continues in either direction. Okay, as long as so that it hits this line. So if you were in this quadrant and that was your terminal side, then what would you do? You would go down here, and that's when you would get a negative tan value. And remember, in this quadrant, tan is negative. Okay, so that's kind of neat. Okay, so let's do an example here. So the point -√5 over 5 and 2√5 over 5 lies on the unit circle and on the terminal side of an angle theta. And we want to find all 6 trig values. Okay, so I'm just going to draw a little picture. So the x-coordinate's negative, but the y-coordinate's positive. So we're going to be in quadrant 2. Okay. So we know the angle is going to look something like, I don't know, something like that. Okay, so this is theta. So the coordinates of this point here is -√5 over 5 and 2√5 over 5. Okay, so we know that the sine theta is the y-coordinate. So that's going to be 2√5 over 5. Cos theta is the x-coordinate, so that's going to be -√5 over 5. Okay, and then tan theta is actually sine theta over cos theta. So we just divide those two. Okay, now the root 5s over 5s are going to cancel, so this is just going to simplify to -2. Okay, then the cosecant of theta is 1 over y, so we're going to flip the 1 for sine, so that's going to be 5 over 2 root 5. Okay, and then if you wanted to rationalize the denominator, you would multiply by root 5 over root 5. So you would get 5 root 5 over 10. Secant theta is going to be 1 over cos theta, so 1 over x. So that's going to be -5 over root 5. Which again, if you wanted to rationalize, is -5 root 5, is actually, it actually simplifies, so it's going to be -root 5, -5 root 5 over 5, so the 5's cancel, it's just -root 5. Okay, now cotan theta is 1 over tan theta, so that's going to be 1 over -2, so -1/2. Okay, so that's all the trig functions. Now I usually line them up because sine goes with cosecant, cosine goes with secant, and tan goes with cotan. So I do the 3 normal ones first, and then the other ones to match. Now if you had a point xy in the plane, being a point on a circle with radius r, which obviously is x squared plus y squared, the square root, centered at the origin, as well as on the terminal side of the angle, then the values of the trig functions are going to be the like we had before. So it's, I guess I could draw it. Okay, so if we have a circle with radius r centered at the origin, okay, so that's radius r. And then we take an angle in standard position. Okay, it doesn't really matter where. So I guess I'll draw it in quadrant 1 here. Okay, so if that's angle theta, so it intersects, so this is the point xy. Maybe I should have done that in blue. Okay, so that's the point xy. So what we would do is we would make our triangle. Okay, so we make our triangle. So this distance here is x, the x value. The height of this triangle is y, and the hypotenuse is r, right? Because our right triangle is over here. So that means just using that triangle, now at this point you can forget about the circle. Okay, so using our triangle, which I did in the beginning, so sine of this theta would be the opposite over the hypotenuse. So that ends up being y over r. Cos theta is the adjacent over the hypotenuse, so that's x over r. And tan theta is the opposite over the adjacent, so x over y. And then you have the other ones, so cosecant theta is r over y, so the flip of sine. Secant theta is r over x, okay, the flip of cosine. And cotan theta is, of course, x over y, so the flip of that. So this works even for bigger circles, so with a bigger radius, but then you just have to worry about dividing by the radius. Now here, you want to also be careful. So the radius shouldn't be 0 because then you haven't used the circle. But the x and y values could. Okay, so this is true as long as x is not 0. Okay, and here I can't have y being 0. Here I can't have x being 0, and here obviously I can't have y being 0. So I never want to divide by 0. If you do, that means that the trig function there is not defined. Okay, so that's what you want to worry about there. So I'm going to leave example 2 for you to try. And let's talk about periodicity. So we say a a function f is periodic if there is a positive number, let's call it p, such that whenever theta is in the domain of f, so is theta plus p, and more importantly, the y value at theta plus p is equal to the y value at theta. Okay, so if you move some distance, okay, the period, then your y value should be the same. Okay, now the first part here just says, so if theta is in the domain, so is. What that just says is that if one of them's defined, then the other one has to be defined as well because their y values are equal. So that actually says the same thing. Okay, and then I guess I should also add the smallest, because this might work for a number of p's. Okay, the smallest such p is called the period of f. I think I already called p the period, okay, but the period is technically the smallest one. So for sine theta, cos theta, secant theta, and cosecant theta, they are all periodic, and the period for them is 2 pi. Okay, so why is it 2 pi? So 2 pi is a full rotation. Okay, a full rotation will bring the terminal side to the same spot. Okay, so another way to say that is, i.e. the angles are coterminal. And remember, coterminal angles had the same trig values. Okay, so if they're coterminal, then the trig values are going to be the same. So sine of theta plus 2 pi, okay, is always sine theta. Cos of theta plus 2 pi is, again, cos theta. All of these, I just want to write 2 pi in. Okay, so 2 pi is the period. Now for tan and cotan, they actually have a period of pi. So 2 pi works for them as well, for the same reason, the full rotation. But there's a smaller one that works, which is pi. So let's just maybe draw a picture. Okay, now this is basically because of where the tan ones are positive. So remember I said that you could think about this line. Oops. So the line x equals 1. You don't have to think about this line, but you can. So if I had an angle, okay, so let's say like this. Okay, so this is the point where it intersects the circle. But this would be the tan value, the height here. So this is 1 and tan theta. Okay, well, if I go, I'm going to get a different color here. Okay, so if I go from here to here, okay, this is theta plus pi, so plus the straight angle. Then I get the same tan value. Okay, so you could also think about this as, oops, I didn't want that. So this point here is xy. This point down here is going to be negative x, negative y. So they're going to have the same tan values. Okay, so if you had, because you're going to take so tan is x over y, or sorry, y over x. So you take y over x, but on this side you take negative y over negative x. That's going to give you y over x. Okay, so they have the same tan values, and it works the same way if your angles go this way as well. Okay, so it actually, tan for them is a smaller period, so it's the actual period. Okay, so tan of theta plus pi is tan theta, and similarly cotan of theta plus pi is cotan theta. Okay, I'm just going to do one of these. So let's say secant of 540 degrees. So that's bigger than 360. Okay, so 540 minus 360 is going to be 180 degrees. Okay, so that's actually equal to secant of 180 degrees. And secant is 1 over cosine. Okay, now 180 degrees is pi. Okay, so that's pi radians, which is the flat angle. And here I'm going to be drawing unit circles all over the place. That wasn't a very good one. Looks more like an ellipse. Oops. Okay, let's try this again. Okay, so there's my circle. Okay, so 180 degrees goes like this. Okay, so that means it intersects the unit circle at this point, and this point is -1, 0. And the cosine is the x-coordinate. So that means that cosine of 180 is -1. So this is 1 over -1, which means that it's also -1 for secant. Okay, I'm going to leave part B for you to try. Now we can talk about even and odd like the symmetry for these functions. So some of them are even and some of them are odd. Okay, so they've drawn here for us, thankfully, theta and negative theta. Okay, now if we think about, we're thinking about the sine and cos and all the trig values of negative theta. And we're going to compare them to what it would be for theta. So let's make our triangle. So that would come down. Okay, this distance here is x, and this length, this is negative y. So, and then the radius. It doesn't really matter, so let's just call it r. So sine of negative theta, so that would be the opposite over the hypotenuse, so that's negative y over r. Okay, that's negative y over r if I bring the negative out front. Okay, so if you think about this top one, it also has x there. Okay, but then this is y and this is r. So sine of theta, not negative theta, would be y over r. So this is actually negative sine theta. Okay, now for cos theta, or cos of negative theta, it's the adjacent, which is x over r. Okay, that's actually equal to, oh, I don't want to write it there. That's actually equal to cos of the regular theta. Okay, now the tan of negative theta is going to be negative y over x, which is negative on the front, y over x, and y over x is tan theta. So that's going to be negative tan theta. Okay, now cosecant is going to be the same as sine, so this is going to be negative cosecant theta. Secant is going to be the same as for cos, so this is going to be positive secant theta, and cotan the same as tan. So what we get, So what we get, so here, let's just say summary. So remember, when f of negative x is equal to f of x, that's an even function. And when f of negative x is negative f of x, that's an odd function. Okay, so our summary is we have some even functions. Okay, the even ones were equal to the positives. So that's going to be cos theta and secant theta. So those ones are even. So they're symmetric about the y-axis. Okay, now the odd functions were all the other ones. So all the other ones are odd. So that's sine theta, tan theta, cosecant theta, and cotan theta. Okay, now these ones are symmetric, or actually I'm just going to write origin symmetry. So they're symmetric about the origin. Okay, now you can use this, these facts to find some trig functions a bit easier. So, for instance, sine of negative 60 degrees, well, that is negative sine of 60 degrees. Okay, so you can pull the negative out front because sine is an odd function. So this is since sine theta is odd. So the negative can come out. And we know sine of 60 is root 3 over 2. So that's going to be negative root 3 over 2. So the way that we would have done this before without using a sine function is we would have found the reference angle, which would be 60 degrees. But then you'd have to know that negative 60 is in quadrant 4 and sine is negative in quadrant 4. Okay, so we have already solved things like this. This is just a new way that's a bit faster. Okay, I'm going to leave these other two for you to try. And that is that's all we have for the trig functions using a circle or a unit circle.